Beneath the surface of the ocean there is a force at work, a force that can create enormous scars on the seabed, suspend millions of tons of sediment in the water column, and sever submarine cables in less than a second. This force is known as a turbidity current. A turbidity current is a type of gravity current. In the ocean, a gravity current is driven by density differences between one section of fluid to another. The difference in density may be caused by suspended material, temperature, or salinity differences. Other types of gravity currents that occur in the natural environment include avalanches, some types of dust storms, lahars, and pyroclastic volcanic flows. In the case of turbidity currents, the density differences that cause a gravity current to occur come from suspended sediments in the water column, usually loosened through geological disturbances, such as earthquakes, volcanic activity, submarine and terrestrial landslides, or the release of gas from hydrocarbon deposits under the seafloor and slope instabilities. There are times when sediments are so built up along the slopes of the continental shelf or submarine canyon, gravity takes over as the walls collapse from the heavy sediment, beginning the turbidity current. Density differences allow the water to become turbid and begins rushing down the slope of a submarine canyon or a continental shelf, picking up the suspended sediments and sometimes carrying the material thousands of kilometers away from where it originated. A turbidity current typically begins on the continental slope and occasionally occurs on the slopes of a submarine canyon and over time is deposited to make up the submarine fan. A gravity current consists of a head, body, and tail. The head is the leading area of the gravity current where particles of larger grain sizes are carried. The tail follows the head and carries the smaller sediment particles. The smaller particles in the water column are able to remain as suspension, feeding the density differences that begin turbid movement of the water, producing a turbidity current. As the topography of the seafloor begins to flatten out, the current begins to lose energy, slowing down as momentum is lost and the head of the current subsides as it is overtaken by the tail. The deposition of material forms what we know as a turbidite. To understand the process of a turbidity current, imagine an avalanche. Beginning with the release of snow and ice by instabilities on the slope of a mountain, the avalanche picks up speed due to gravity and density differences between the air and the snow. The material races down the mountain slide at high speeds, picking up everything in its path. Just like a turbidity current, an avalanche begins to lose energy as the terrain flattens out. This allows the debris to settle out as the momentum is lost from the flow. Turbidity currents are an integral part of the submarine environment. They are a major agent of sediment transportation and therefore one of the most significant ways for sediment to be deposited in the deep sea. Turbidite systems also form a significant component of the stratigraphic record and include many of the world's most significant hydrocarbon reservoirs. Turbidity currents can also cause environmental hazards such as reservoir sedimentation, submarine cable breakage, and pollutant dispersal. Events such as these have happened all throughout geologic history all around the world, many that have been earthquake-induced. On the west side of the Pacific Ocean, the 7.1 magnitude earthquake occurred off the southwest coast of Taiwan in 2006. This triggered a turbidity current that caused 11 submarine cables to break between 1,500 and 4,000 meters deep off the southwest coast of Taiwan. This turbidity current reached a maximum speed of 20 meters per second, or 45 miles per hour on the steepest slopes. Other areas around the world that have experienced turbidity currents include the Grand of Newfoundland. In 1929, when a 7.2 magnitude earthquake triggered a turbidity current. This caused 12 submarine telegraph cables to be snapped as it flowed for over 400 miles. Also, along the Cascadia subduction zone, scientists have discovered different turbidites all along the plate boundary stretching from Northern California to Vancouver, Canada. These deposits have been dated to correlate with earthquake events that happened during the Holocene. A turbidite is the deposit found from a turbidity current. A turbidite can take seconds to years to settle out and can extend from kilometers to thousands of kilometers, consisting of gravel, sand, and mud. In the case of the turbidity current occurring off the coast of Newfoundland in 1929, the deposits covered well over 280,000 kilometers and were 100 centimeters thick. The Bouma sequence is the ideal depositional sequence of a turbidite. It is named after the scientist Arnold H. Bouma, whose research findings in 1962 identified the sequence in turbidite deposits. This finding has been cited as being a geological milestone of the 20th century. There are 5 layers in the Bouma sequence, denoted A through E. The first layer to be deposited, A, is massive sand with a gravelly base. This layer finds upward, meaning the coarse grains are at the bottom and the finer grains are on the top. The coarser grains on the bottom can range from pebbles to boulders. Turbidity currents have been known to carry cars and other large debris. Coarser grains settle out first, typically at the base of the submarine canyon because they are the heaviest and need the most energy to move. The next layer to be deposited, B, is parallel laminated sands. The parallel laminations are created from the high energy of the flow. The next layer to settle out, C, is cross-laminated sands with ripples. The ripples form because the flow is slowing down, which allows the ripples to be formed and preserved. In layer C, we may also see convolute laminations, which are formed by the expulsion of water from rapidly deposited sediments. Layer D is laminated silts that sometimes show bioturbation. Bioturbation is the reworking of soils and sediments from animals and plants. What is seen in this sequence is trace fossils of burrows from benthic animals. Layer E is last in the sequence and is a settling of mud that was kept in suspension during the turbidity current that is able to settle with time. If these turbidites were deposited in the deep sea, how is it possible that they end up here on the beach, in our own backyard? Understanding plate tectonics can help us answer this question. When 2 tectonic plates converge, this causes subduction as well as uplift, bringing the turbidites to the surface for our visual pleasure. Let's take a look at some real examples of turbidites found in Central California that have been brought here by uplift. By looking at the outcrops, geologists can piece together the story about how the turbidites were formed. Different layers of the Bouma sequence can be seen in the stratigraphy of the sediments. Sometimes, when looking at turbidites in the field, we do not see all of the layers in the Bouma sequence. You can imagine that if you look at a cross-section of a turbidite on the seafloor, you would see layers A through C closer to the submarine canyon base, like these deposits seen at Point Lobos Natural Reserve. At Point Lobos Natural Reserve, turbidites can be seen embedded within massive conglomerates that were deposited by a debris flow. Here, we clearly see the change from layer A to B to C. Layers D through E are usually seen farther out at the edge of the submarine fan and the levees along the submarine canyon channel, which can be seen along the Northern California coast. Previously stated, the Bouma sequence is rarely seen deposited in nature because of the chaotic, high energy of the turbidite deposition, which can remove underlying layers of sediment so an incomplete sequence is deposited. You can see in this picture that there are some chunks of the D and E layers inside the debris flow deposit. This means that when the mass gravity flow was traveling downhill, it scoured out the top layer of the previous flow and was deposited with the new sequence. Turbidity currents are a powerful force that can move all of this and even more sediments and deposit kilometers away from the source. Turbidite systems and deposits found in submarine fans contain valuable information about past climate and depositional processes. Turbidites from past currents assist scientists in understanding these events that have rarely been directly witnessed in nature. Deposits from turbidity currents can also be indications of tectonic and other geological activity and sometimes even become storage units for hydrocarbons beneath the surface. These powerful currents can even rip up past deposits from the seafloor and erode large areas, creating underwater canyons. It is important to know about and understand these massive currents because of the integral part they play in the marine environment and sediment deposition in the deep sea. Turbidity currents are just another powerful process under the waves of the sea.